So I'm Elwaz Abloki with Patrick Bord, and this is our work with Benjamin Piwowarski, Laure Soulier, and Patrick Gallinari. The work is titled Context-Aware Zero-Shot Learning for Object Recognition. So let's start with some background on the zero-shot learning recognition task. So in this task, the aim is to classify unseen objects by leveraging auxiliary knowledge. So you have two sets of class. The classes that consist the source domain, which are classes for which you have training images, and the target domain, which contain the zero-shot classes for which no training images are provided. And so the aim is to recognize objects of the classes of the target domain, and this can be done thanks to embedding every classes in a shared semantic space, typically learned with textual resources. So the canonical approach for this task is as follows. So for training, a mapping is learned to project images of the source domain to the semantic space with a triplet loss. And at inference, images of the target domain are projected to the semantic space, and the correct label is returned by taking nearest neighbor of cosine similarity. So we can look at this task a bit differently. So we have textual corpora from which we can learn a semantic space, and within this space, we can ask the question, what does an object look like? And this is the core intuition of zero-shot learning. But we would also would like to use contextual information. So language can tell us that a tiger has stripes and an orange fur, and this can help to recognize a tiger within an image, even though tigers have never been seen before. But language also tells us contextual information, typically that tigers can be found in a savanna, nearby antelopes, or in a zoo. And if one can recognize a zoo in an image or antelopes, then this might tell us that the unknown object might be a tiger, thanks to this contextual information. So this is the motivation for our work, and basically was the question, is information about possible visual environment of objects contained in language and in this semantic space, and would like to use this visual context information for the zero-shot recognition task. And a complementary orthogonal research question is whether or not information about the visual occurrence frequency of objects in images is contained in language, and this would help to deal with imbalanced class distribution in the zero-shot recognition setting.
So now we're going to present our context-aware zero-shot learning model. So our goal is to model the probability of a class I given V, the visual area of interest around the object, and C, the visual context in the image. So we make the simplifying hypothesis that V and C are conditionally independent given the class I, and this enables us to model P of I given V and C as a product of three terms, one visual term, a context term, and a prior term. So in this example, we have an image of a man cooking in his kitchen. In the blue box, we have the object of interest that we want to find. We don't know its class. Here it's apple. And around this object, we have context objects that belong either to the source domain, so we know their classes, or from the target domain. In this example, the visual component ranks tennis ball as first and apple as second. But here it's the context component which is discriminant, because in this particular context, apple is much more likely to be found in this kitchen environment. So that helps the model to make the right prediction at the end. So now we're going to detail our three components. So first, the prior component. Its goal is to assess whether an entity is frequent or not in the data set. So this component doesn't take the image into account. It just takes W, the label embedding of the candidate class, applies an MLP on top, and so that is how we model the log probability of the prior component. The visual component is pretty classic, inspired by the device model. So what we do is that we take the visual area of interest V, we apply a CNN and linear layer to compute a visual representation F of V. Once we have this representation, we compute the cosine similarity between this visual representation and our label embedding. And this is how we model the log probability of the visual component. Lastly, the context component. So here it doesn't take the object itself into account. It looks at the context. So we compute a context vector HC that I'm going to detail in the next slide. We concatenate HC with W, the label embedding, and we apply an MLP on top. And this is how we model the log probability of the context component. So now I'm going to explain how to compute the context vector HC. So here in this example, the object of interest is a mouse. Around it we have object boxes. So we suppose that boxes are defined in our model as input. We have either objects from the source domain. So for these objects, we know their classes, so we can use word-to-vec embeddings. We can also use CNN representation, so visual representation. In green, we also have objects from the target domain. So we don't know their classes. We can't use their word-to-vec embedding, but we can use their visual representation. So once we have computed the word-to-vec representation or CNN representation, we can choose which source information we want and average all these vectors to form the global context vector HC. So how do we learn the parameters of our separate components? So first, the prior component. What we use is a triplet max margin loss. We sample the negative examples from the uniform distribution to ensure that if an object is more frequent than another, this order is preserved. In the context and visual component, we also used max margin triplet losses, but in that case, we sampled the negative from the true data distribution because we don't want these components to focus on the frequency of objects, but rather on the context and visual information itself. So now that we've learned the log probabilities of the various components, but up to a certain normalization constants, which may depend on the class I of the object. So what we did is that we plotted these 3 log probabilities in a 3D graph. In blue are incorrect configurations, in red are correct configurations. We observed that the delimitation is linear, so the probability P of I given V and C writes very simply as follows with a log linear relation. So the normalization constants, we can make the hypothesis that they are scalars, and they can be found via cross validation. So concerning the experiments, we didn't use the classic the short learning data sets such as AWA, Cub, or Sun. Rather, we used visual genome quite logically because this dataset contains very rich contextual information, around 21 instances of objects per image. So it contains roughly 100,000 images and 5,000 unique objects. It's quite an imbalanced dataset because 10% of the most frequent classes make for 84% of instances. And how do we build the source and target domains? We first fix PSOP, the percentage of source objects, so scene objects compared to the total set of objects. And once this PSOP is fixed, let's say 50%, we randomly split the set of classes into target objects and source objects. And concerning the evaluation, we used a ranking metric called normalized mean first rank. So with this score, the lower, the better. With the perfect model making a 0% score and the random model a 100% score.
Now we can look at some results. So here, every row represents different models. So on the left, you can see which probability these models represent. And so we're more focused on the target domain T, and the 3 columns in the target domain depend on the amount of objects we have in either the source or the target domain. So 10%, remember, means that 10% of objects are seen and 90% are unseen, which is much harder than having 90% of objects in the source domain and 10% in the target domain. So first, what we can observe is that the visual occurrence frequency of objects can be learned from textual semantics, as the model as just predictions of the prior component is much better than a random baseline. Now we can see that contextual information is also useful, as adding the information from the context component improves the results. Quite logically, we observe that the more objects are contained within the source domain, the bigger is the improvement for the performances, as the context gets richer and more data can be used in the source domain. And last but not least, the contextual information is complementary to visual appearance of objects, as we have an improvement, a relative improvement of 10 to 15% between the model which uses contextual information with respect to the model which does not. Now we can discuss the different ways to model, how we model contextual information. So on the left is how we model the contextual objects that belong to the target domain. On the right is how we model contextual objects of the source domain, for which we can either use the word-to-vec representation of the label or CNN representations. So the results are that increasing supervision helps, okay, which is quite logical. First, when bounding boxes are available and that we can crop contextual objects from the source domain, when more objects are, when objects are labeled, so that we can use the label representation instead of just looking at the raw pixels. When more context objects are used, so for example, when we, in addition, consider a contextual object of the target domain, and also when low-level information is used complementarily, that is for the object of the source domain, we both use the pixel information and the label representations. So this gives us the final model, which has a 22% relative improvement over the baseline model, which does not look at context. Let's look at some qualitative results. So on the first image, we have a boat in the blue box, which is the object to be predicted. Then we have the outputs of each of the three individual components, and on the right is the predictions of the global model. So we can see in this example that the boat is very small and hard to recognize by just looking at the region, and which leads P of V knowing the class that to make a poor prediction. But the contextual component is pretty good, thanks to having a lake around, clouds and trees, and this gives a final correct prediction for the global model. Now, if I show you this cherry-pick example, I also need to show some examples where the context can degrade performances. Typically, when an object is unexpected, such as on the bottom of the slide, we have books in a kitchen, where on the far right we have the global model, which predicts that books are at the 40th rank, but the same model without contextual information correctly returns the book label. And this is because books are quite unexpected in the kitchen, and we see that the contextual component rather puts freezer, oven, and so on objects. Now we can also investigate per class, which classes benefit the most from the context. So we plot the rank distributions as a box plot for several classes. So in blue is the global model with contextual information, and in red is the rank distribution on the test set for the model which does not look at the context. We can see that the contextual information can help to refine predictions. For example, in the case of the player, where context helps, a player without context is just a person, but by looking around and seeing a helmet, baseball, and so on, leads to ground the person in a sport environment and hence to help predicting a player. Context can also help to disambiguate generic shapes, such as a handle, which is just a round object if we just look at the handle, but seeing around a door, a cabinet, or a fridge helps to disambiguate this round object to the particular class of a handle. This does not come without limitations, and for example, in the case of house and dirt, contextual information can hurt, and this is because these are objects which can appear in a wide variety of different contexts, and we found that the more unique context an object can have, the lesser is the contribution of the context.
So, in conclusion, we showed in this work that first, leveraging visual context improves the zero-shot recognition task. Second, that visual context and priors can be learned or contained within word representations. Our perspectives would be to first remove the need for bounding boxes, because here the bounding boxes are given as input to the model, and second, to learn grounded semantic representations that include more visual context information. Thank you for your attention. Please come to see our poster number 131, and if you have any questions, we'd be happy to answer.
Any questions? Please come to the microphone. So I have a question. Did you try this out to see if it would transfer to any other data set or any other data? Or is there a risk that it overfits to this data set that you trained on?
Well, thank you for your question. So the problem we have is that we need data sets with lots of context, so we cannot really do this on typical data set. We just have a unique object centered in the image with no contextual information. So we did not try on other data sets. I think Open Images has scenes with lots of objects. We should try on that one, but no, we did not try that. So the question is, how about temporal context, and typically in the case of videos? So yes, I think it's, indeed, we could use temporal context from videos, as well as we could use spatial context in the case of images. So that would mean that spatial information should be contained within the semantic space that we learn only from language, so which could somehow be possible, and then use this spatial linguistic information and transfer it to the visual data. So yeah, in the case of spatial for images, I think it's possible. And in the case of temporal for videos, I have the same intuition, but
I don't know.
So this needs to be contained in the semantic space at first, which is learned beforehand. That's the main challenge.
All right, let's thank the speaker again.
So hello everyone, my question today is how can we make CNNs more adaptive in terms of performance? I'll present to you our band-limited training and inference for CNNs. So my name is Dziedzic and I'm from University of Chicago. This is joint work with John Paparizos, Sanjay Krishnan, Aaron Elmore, and Michael Franklin. So natural images and in general natural data are biased towards lower frequencies. On the left-hand side, we show a natural image in the spatial domain. On the right-hand side is the same image, but in the frequency domain. We can go back and forth between these two different domains using Fourier transformation and its inverse. We also show on the right-hand side how we can compress the image in the frequency domain, in this case by 50%. Our main contribution is a method for convnets to constrain the frequency band in convolution operation, and we are focused on efficiency, but also we want to leverage the properties of frequency domain. And we show on the right-hand side how we can compress the image in practice by 50%. So FFT-based convolution for convnets was proposed first by Mathieu et al., and then it was refined by Vasilash et al. So how does it work? We have as inputs data x and filter y. We apply FFT to go to the frequency domain. In the frequency domain, we execute element-wise multiplication, which is convolution, and then we go back to the spatial domain using inverse Fourier transformation and return output, that is data x convolved with filter y. However, the main problem with this algorithm is that it uses substantial memory workspace. So the question is, how can we do better? In our work, by band limiting, we define masking out high frequencies. In the red boxes, we indicate where we band limit data x and filter y in the frequency domain. We discard high frequency coefficients. So in the red boxes, we use less memory. Next, because we have fewer coefficients, they require fewer multiplications, and we can accelerate the multiplication indicated in the green box. Additionally, we have to make sure that we preserve enough of the spectrum so that our models can retain high accuracy. What is our band limiting technique? Let's imagine that we have FFT input map. And because of conjugate symmetry, we can discard almost half of these coefficients, and they can be reconstructed from values in white. Next, we have real value constraints. And we make sure that during our compression decompression, we maintain these values as real values. There are no constraints for values in blue. However, if you want to fully recover this FFT map, you have to preserve the yellow and blue values. Our compression is lossy, and we start from removing the high-frequency coefficients. The first layer of compression is indicated in the red boxes. We remove this first layer of compression. If we want to compress more, then we remove data that is in green boxes. And we proceed in this fashion, starting from the corners and going towards the center of the FFT map. What is the impact of band limiting on accuracy? Here we present on the y-axis test accuracy from 85 to 95%. On the x-axis, we systematically increase the compression rate from 0 to 80%. Our model is ResNet 18, trained on CIFAR10 data. For the full spectrum model without any compression, our accuracy is 93.5%. If you compress our model in the frequency domain by 50%, our accuracy drops slightly to about 92%. We observe similar trends for other datasets and models. We also present result here for DenseNet 121 model, which was trained on CIFAR100 data. What are the main takeaways from our band-limited CNNs? So we propose a method to constrain the frequency band in convolution operation. Our models degrade gracefully, and we have this tuning knob that we can sacrifice slightly the accuracy for a better performance in terms of faster computation or lower memory usage. And we observe that during training, low frequencies are learned first, and to get the best accuracy, we have to apply the same compression during both training and inference. We also found that our band-limited models are robust to some attacks, in this case, black box attacks. For example, if adversary injects Gaussian or uniform noise, then we can reject this noise and recover the correct label. Finally, our method is applicable to other domains, such as time series and speech data. Thank you very much, and please come to my poster session. ID is 132.
Hello everyone, thanks for coming. I'm Peng Kai from Boston University. I'm glad to present the work in our group learning classifiers for target domain with limited or no labels. So there are many scenarios in machine learning problems where you have a lot of annotated data in your source domain, but you come across with target domain where you only have limited access to its examples or labels. Such as zero-shot learning, you may have a lot of annotated dogs in your source domain, but you need to classify cat, which you don't have any example. Or maybe few-shot learning, you have a few or one or two or three examples for this cat, but you still want to classify it. And in these cases, it's almost impossible for you to train your model from scratch. So the better way to do it is trying to adapt your existing models you trained from your source domain to this new environment. And our goal in this paper is trying to learn a static and universal representation, which is robust to this kind of domain shift. So therefore, we propose the low-dimensional visual attributes encoding as our solution. So to get this encoding, your image, which contains the object, is firstly inputted into this part attention model, which gets the high-dimensional visual features for each attention or part. Then these visual features will be projected into the low-dimensional visual attributes encoding by using the part-featured encoder. And the LDV encoding in each part is in fact a probability vector, and this probability vector denotes the probability of this specific part belongs to all the prototypes in the part. Like the example here for the red feature for the bird head, it has 79% of type 1 and 3% of type 2 and 1% of type 3 and even more for the entire data set. So that to ensure this happens, we use this part feature decoder to reconstruct the original high dimensional visual feature from our LDV encoding and all the representations for the LDV and all the representations for the prototypes in each part. Therefore, By using this autoencoder structure, we can learn the LDV encoding for each example and the representation for all the prototypes in each part simultaneously in the training time. And after it's learned, during test time, you can input this LDV encoding in any task-specific predictor to make the final prediction. For generalized zero-shot learning, we can project this encoding into semantic attribute space. For future learning, a simple nearest neighbor classifier can be used to classify as all those new classes. And for domain adaptation, since all the classes are the same along the source and the target domain, you can use a simple classifier to make the final prediction. Okay, so in summary, the low-dimensional visual attributes encoding is trying to encode every object into a mixture of part prototypes. And why could it help with all our problems? First is it's low-dimensional because the number of prototypes in each part is limited. And as long as your prototypes in each part is descriptive enough, then every class can be represented uniquely, making this encoding very discriminating. And also in our experiments, we observe very small intra-class variance for the encoding, and the encoding is very robust to domain shift. Here we give an example of the learned encoding for the digit data set. As you can see from the right side, the same class, digit 2, has very close LDV encoding, even though their visual appearance is quite different. This is because the underlying existence of all those prototypes in each part is stable, even though how much do you distort this visual appearance of your class, such that it's robust to the domain shift. And in addition, this embedding mirrors how human label the semantic vector, and it can encode unseen classes by the prototypes you learned from the seen classes, which is good to the future learning and zero-shot learning. And finally, it requires less data and feedback from the target data set, from the target domain than all the other methods. So we evaluate our methods in all the 3 tasks on many benchmarks, and the results shows that our method with this LDV encoding can reach comparable or even better results than all the other state-of-the-art methods. So in the take-home message of our contribution is that compared with all the other methods, our method append an additional part encoder which projects the high-dimensional feature from the every attention into the low-dimensional LDV encoding. And for more details and any questions, please come to our poster at number 133. Thank you.
Hi, I'm Daniel, and this is joint work with Eric Liang, Ian Stoika, Peter Abiel, and Peter Chen. We introduced population-based augmentation, or PBA, an algorithm that quickly and efficiently learns a state-of-the-art approach to augmenting data for neural network training. PBA matches the previous best results on the CFAR and SVHN datasets, but uses 1,000 times less compute, enabling researchers to effectively learn new augmentation policies using a single workstation GPU. You can use PBA broadly to improve deep learning performance on image recognition tasks. Data augmentation is a strategy that enables practitioners to significantly increase the diversity of data available for training models without actually collecting new data. Data augmentation techniques such as cropping, padding, and flipping are commonly used in training large neural network models. However, most trained models only use these basic types of augmentations. Recently, Kubik et al. With Google has been able to push the state-of-the-art accuracy on image recognition with auto-augment, a new technique to automate the application of diverse data augmentation operations. Auto-augment introduces 16 geometric and color-based transformations and formulates an augmentation policy that selects up to 2 of these transformations at certain magnitude levels to apply to each batch of data. These higher-performing augmentation policies are learned by training directly on the data. What's the catch? Auto-augment is unfortunately a very expensive algorithm that requires sampling up to 15,000 models to train to convergence in order to generate a reinforcement learning-based policy. No computation is shared between samples, and it costs 5,000 GPU hours to learn a CFAR 10 data augmentation policy using auto-augment. If using Google Cloud P100 GPUs, this would cost around $7,500 just to learn one policy. Our algorithm, population-based augmentation, learns a similar performing policy, but using 1,000 times compute to do so. We formulate the problem as hyperparameter search and only need to train 15 models to convergence. Our learned augmentation policy adapts and adjusts based on training progress. We learn an augmentation policy by training several copies of a small model on a CFAR10 data, which takes 5 hours using a Titan XP GPU. This policy exhibits strong performance when used for training from scratch on larger models and also when transferred to train on CFAR100 data. The models we evaluate on include wide ResNet, shake, and PyramidNet with shake drop. You can see the power of augmentation by comparing to baseline performance shown in blue, which only applies the basic augmentations of flipping, padding, and cropping. Relative to the several days it takes to train large CFAR10 networks to convergence, the cost of running PBA beforehand to learn an augmentation schedule is minimal, adding only around 2% compute and wall clock overhead. We leveraged the population-based training hyperparameter search algorithm by Jitterbrook et al. To learn probability and magnitude hyperparameters for each augmentation operation. Each population worker trains on a target dataset and learns a candidate hyperparameter schedule. The best schedule is then transferred to train larger models from scratch. We use a combination of evolutionary methods and random search. At frequent intervals, a process exploits high-performing workers by copying their model weights to lower-performing ones, and then explores by perturbing the hyperparameters of the worker. Through this process, we are able to share compute between the workers and avoid the cost of training thousands of models to convergence in order to reach high performance. Our learned policy schedule can adapt based on a current epoch of training. This is in contrast to fixed augmentation policy like auto-augment that applies the same policy independent of the epoch number. We designed PBA to naturally adapt the augmentation hyperparameters to gradually increase in strength over time. You may be able to see this in the figure, which shows PBA applied during different percentages into training. Simpler augmentations may help the network learn faster earlier on, while stronger augmentations can be a counter to overfitting later in training. Our code is open source on GitHub, so ordinary workstation users can easily experiment with PBA. Please visit our poster number 134 today. Thank you.
Hi everyone, I'm Tom. I will present our paper about anomaly detection with multiple hypothesis prediction today. This work is supported by my University of Freiburg in Germany and the company Bosch. So the task of anomaly detection is needed when a subset of classes is extremely rare, or even the extreme cases for when some classes are unknown at the training time. So typically, people try to learn to approximate the normal data distribution and measure the difference between the input and the reconstruction at test time. However, input images are quite high dimensional, as you know, and capturing the complete data density distribution is more difficult than the anomaly detection task itself. It is also very data intensive, and it requires a lot of normal data to capture the distributions. So typically what people do is they use autoencoder and then capture the normal data distribution, and at test time, they compute the difference. And in most of the time, the blurry reconstructions have the highest likelihood under this model. So, which means that after you have learned, put a lot of effort into learning the model tells you the blurry image is the most likely data point you can have. But if you think about that clearly, the blurry images do not appear in the data sets, so they should be themselves anomalies, right? And here you have a sample. So on the left bottom, you see an anomaly data point, and the reconstruction of the variational autoencoder is quite blurry. So in the end, the anomalies is not really visible. So it's quite bad. And we figured out why that happens, and we proposed a solution, which you can see on the right. Our reconstruction is very close to the input image, and in the end, you see the anomaly much more clearly. So the intuition behind this is the autoencoder creates blurry reconstructions because the decoder has to overage between multiple modes. So the modes are the dense regions in the conditional input space. So that means if you input an image into the autoencoder, you go into the latent code, and then you have to decode it again, right? But the decoder tries to decode it, but it's not really unique. So there are multiple solutions which can be the reconstructions. And since the decoder has only limited capacity, it has to overage between the different modes. And what we do instead is we try to capture this multiple data modes with so-called multiple hypothesis networks, which is very simple. We just add different heads to the decoder. So now the decoder can do multiple guesses. And the problem is, well, hypotheses could support non-existing data modes, so we have to make sure that they are generating something meaningful. And furthermore, we need to cover as many data modes as possible, otherwise we land in the same problem again, that we only learn the overage data mode. So in this framework, it's still not suitable for anomaly detection. So we also propose some other techniques. So we do adversarial regularizer to make sure that the hypotheses generated are somewhat meaningful by using an additional discriminator here, which is very simple. You kind of take the hypothesis network output and put it into a discriminator, and it should be as real as possible. So you try to follow the underlying data distribution. So for anomaly detection only, there is a slight change. We train an autoencoder now with the additional GAN. At test time, it's kind of the same. So, and on different benchmarks, we improved previous works by some margin, and our results are also showing that our approach is more stable. So please visit our poster. It's the ID 135, and I'm happy to answer your questions in the poster session. Thank you.
My name is Vitawat. I'm from Max Planck Institute for Intelligent Systems. So today I would like to tell you about a new approach to generate images that are similar to a set of images that you give. And this is a joint work with great colleagues from both MPI at Max Planck Institute and Georgia Tech. Okay, so let me start with the motivation of this work. So modern generative models take the form of an implicit model. So an implicit model is one where you first draw a latent code or latent vector Z from a simple distribution like multivariate Gaussian, and transform it by a deep neural network, G. And GZ is your generated sample, typically an image. So a well-known class of this model is generative adversarial networks, which have been shown to be able to generate realistic images, like this one, for example. This is again trained on Elson Tower, so you can generate a whole bunch of towers. Now, a problem is there is really no control over the generative process. So what if I want to generate more towers like the one on the right? So there's no way to do this easily. And this is the problem that we tackle in this work. And this is what we mean by a content addressable image generation, or content addressable GAN, CAT GAN. So the goal of this work is to make any pre-trained GAN models content addressable. So we propose a procedure which adds content addressability to any given implicit model, G, without retraining. And here's what I mean. So here you can give, say, these two images as your input. So M means the number of input images. And this is an example of the output from our procedure. So 3 output images. You can see that the three images are highly consistent with the 2 input, and they're also not redundant. They're not like the same images repeating. And here's another case. And M and N are allowed to be arbitrary, so any number. Okay, so the idea of our proposed method, which we call CAT GAN, content addressable GAN, is the following. It's very simple. So the idea is to generate images from G. So G is your generative model, so as to match the mean feature of the input images. But this matching takes place in reproducing kernel Hilbert space, RKHS. Okay, say let's consider an abstract infinite dimensional kernel space, like there. And these 3 input images are represented in blue, so 3 input. And this is the mean of the 3 input images. So the idea is we have a generative model G, and the output range of G is represented as this black line. So the idea is to optimize or find output images in this range so that the mean of the output matches the mean of the input. And so in this picture, the 2 means match completely. So that's the basic idea. So mathematically, this is how you do it. So we optimize, we minimize, we find y1 to yn, these are output images, constrain them to be in the range of G, and the objective function is as following. So the first term here, this is the weighted mean of the input images, where xi is the ith input image, and phi is just an infinite dimensional feature map, which will be induced by a kernel. I will show you later. And this is just weighted mean of the input. And the second term, that's the mean of the output images. And the goal is to find y1 to yn. So, and the weights, so okay, so yeah, I said weighted means, so the weights, w1 to wn are manually specified. So in the case where you have no preference, so wi encodes the importance of the ith input image. In the case where you don't have any preference, then you can just set it to be uniform weights, 1 over m. But you can do interesting things. I will show you later. Okay, so first, let us rewrite this objective. This phi is an infinite dimensional map. You can simplify this objective by doing the following. First, we will expand this square. We will get 3 terms. The first term is going to be the square of the first term in this distance here. So here, this angle bracket, this is just an inner product in a kernel space. And that's the first term. The second term is going to be the square, self-inner product of this second term here. And the third term, that's just cross term, right? -2 cross term of the 2. So now, the inner product is bilinear. Bilinear means it's linear in both arguments. So meaning that you can actually take out the sums and the weights to be outside the inner product. And by doing that, we get this objective. Okay? So now we see that this objective only involves inner product between phi xi and phi xj, or phi a and phi b, where a and b are 2 images. So we can actually define a kernel function. So kab, define it to be the inner product between phi a and phi b. You can just think of this kab as some kind of similarity measure between 2 images, a and b. And now remember that we also want the output images to be in the range of G. So to implement this, you can just parameterize the output image, say yj, to be gzj, where zj is some latent vector, which we will optimize. And by doing this, all the output images will be in the range of G. Now, if you substitute these 2 expressions into the objective, then the objective looks like this. Okay, so now it doesn't depend on phi. It's kind of implicitly defined by the kernel function k. And in fact, this objective has a name. It's known as the maximum mean discrepancy, or MMD. And this is the MMD between the 2 sets, input and output, the input set and output set of images. And in our approach, CAD-GAN, it directly finds Z1 to Zn, directly finds the latent vectors for the output images by minimizing this objective that you see here with Adam. And notice that the first term is actually independent of Z. So you can drop it when you do the optimization. The third term, this one, encourages relevance. So to see this, notice that this is nothing but just weighted mean of the similarity between input and output images, right? And we want to minimize the negative of this, so meaning that we want to maximize the similarity between input and output images. Now the second term there encourages diversity because this is just the average similarity of among the output images, right? And we want to minimize this. So minimize the sort of redundancy in the output images. Now, that is our objective. Now, but it depends on this big K, which I haven't told you how we set it. So K in this work is required to be a positive definite kernel, and we propose setting big K to be of this form, where E is an image feature extractor of your choice, which could be VGG face if you are dealing with face images, or could be places 365 if you are dealing with outdoor scenes, for example. So E is an extractor of your choice, and small k is another sort of kernel, but now kernel on top of extracted features. And in this work, we propose using the inverse multiquadratic or IMQ kernel for the small k, and the IMQ kernel takes this form for some C. We empirically found that this kernel gives realistic images from our procedure. Okay, so that's the end of the theory section, and I will now show you empirical results. So let's consider, the first one is this one. Let's consider a GAN from Mesquita and colleagues from 2018. This is a GAN trained on Elsan bridge. So this GAN model generates all kinds of bridges, as you can see. So these are samples from GAN, unconditional samples. This is not the output of our procedure yet. This is just normal samples. Now, to demonstrate our procedure, we set E, the feature extractor network, to be places 365 ResNet. So places 365, this is a neural network. It's actually a classifier, for, and the output is 365 dimensions. Each one corresponds to one kind of scene, outdoor scene. Okay, here's the input images, and that's the output. So one interesting thing about this case is we didn't actually constrain the color. The color is just black and white, and we didn't do anything. We just got this. And also the 3 output images are highly consistent with the 2 input images. Here's another case where we have a bridge with trees, and the output images also contain bridge with trees. And also 2 more cases. Another example is a GAN trained on Elsan bedroom. So this is a bedroom GAN, and it can, again, generate all kinds of bedrooms from the same authors, Mesquita and colleagues. And this time, to demonstrate, we ask for 6 output images. So N is now 6, and these are 4 separate cases. So notice the tone and texture. For example, in the first case, so here there's some sort of like black and white stripe there, and in the second picture there's kind of the like brown background, and both texture and color are present in the set of output images. And this holds true for all 4 cases. Like in the second one, we have like pink bedroom and so on. Okay, so one interesting thing you can do with this procedure is you can actually set N, the number of output images, to be smaller than M, or the number of input images. And this task, we refer to it as the compression, because we kind of compress the information in the input set to be sort of somehow smaller, because we have smaller number of output images. And by doing this, it will encourage feature combination. And the reason for this is because, so if you think about it, in this case, we have 2 input images and 1 output. We are optimizing this single output image. It is somehow to be able to reduce the error but to be able to match the mean of the input images. Somehow it has to combine the features from both. And there's only 1 image, right? And therefore, this 1 image here, this output, will contain some visual features of both. And as you can see here. So these are 3 separate cases. You can also do this one. So you can also emphasize one input image more than the other one. So remember W1 to WM. I haven't talked about that. So the result so far, we set WI to be 1 over M, so just uniform weight. So now you can actually tweak this W to put some emphasis on certain input images. And if you do so, you can do something like this. So in this case, the 2 input images are shown on the far left and far right. And for each value of W, ranging from 0 to 1, we generate 1 image. Okay, so 2 input and 1 output. But we cannot change the weight. So as you can see, as the weight W1 reduces from 1 to 0, the importance of input 1 also kind of disappears, right? And this holds true for these two cases as well. So these are three independent cases. It actually gets more interesting when you consider three input images. You will get this kind of triangle. So when you have three input images, there are three weights, so W1, W2, W3, but because of the constraint that they have to sum to 1, we only need to tune W1 and W2. And so here, the three input images are shown at the corners with borders, and we vary W1 and W2, the two weights, and these are the results. So one interesting thing to note is that this picture here on the bottom left, this is frontal face, and the X2, this face showing the right part, and then X3 is showing the left part. And as you can see, as the weights, W1 and W2 change, the output images come somehow the face turn, right? That's one interesting thing. Last example is this one. Let's see, okay, yeah. Last example is this is just to show you that our procedure can also generate a new Avengers agent by combining, I think this is Nick Fury and Iron Man, and also Mark here. So notice that, okay, I think in both examples, notice that the background is not really respected, right? Like this one, for example, this one actually has blue, but everything is black here. The reason for that is because we believe is because of the E, the extractor. Here we use VGG face as the extractor, and we believe that it doesn't really care about the background. It only cares about faces. That's why somehow the background is not respected. Okay, so to conclude, we proposed a kernel mean matching procedure for content addressability of GANs. And the procedure allows us to generate images that are similar to set of input images. And we do this by kernel moment matching or kernel mean matching. So if you'd like to know more, please come to our poster tonight, number 136. Thank you.
Hi, everyone. This talk is basically about reverse engineering machine instructions for industrial knitting. So industrial knitting machines, such as that one, are pretty complex machines that allow you to generate full garments from scratch. Basically, you program the machine, then you press on the button, and eventually you end up getting your sweater fresh out of the machine straight away. Here you can see some of the needles on the machine. Those needles can all be individually controlled. And so first, why do we care about knitting? The first reason is that many garments are knitted. Beanies, scarves, gloves, socks, you can all knit them. And then the second reason is that on those garments, you can see various types of patterns, and with those machines, you can fully control the shape as well as the patterns, which means that from the user perspective, we can do lots of customization. And actually, it's kind of surprising that this is not readily available already. The main reason for why you don't see that in your shop next door is that you need to program the machine. And programming those machines is very hard. It requires skilled experts. But there's a good news, which is that there are many people who know about patterns, especially all the people who know about hand knitting. And so we come here and we are trying to automate the programming of those machines. So imagine you see one of your friends has a great new sweater with great patterns. You take a picture of that pattern. Then our system is going to reverse engineer the machine instruction needed to get that pattern. And then you can reuse it for a new pattern on a new sweater or some other project you have in mind. To do that, the first thing we had to do is to figure out a new domain language for pattern knitting. The main reason for that is that those machines can do lots of other things and not just patterns. And then, of course, we need data. So we created a data set. And as you can expect, we will never get enough real data. So what you get is to not only have pairs of real data samples with instruction, but also synthetic samples that are made by using yarn simulations. So the learning problem is basically mapping images to discrete instruction maps. That's kind of standard, but then we have two domains of input data. The question is, how do we best combine both? So we have an ideal minimizer, H star, then we have our empirical minimizer that is going to combine the two sources of data. And of course, as you can expect, there is a bound on what we can do. The bound contains some term epsilon that is based on the hyperparameters. Then we have the ideal error that we cannot really do much better because it comes from both of the sources of data. And finally, we have the discrepancy between the two sources of data. And that's what we are focusing on in this work. So two sources of data, the real data on the left, the synthetic data on the right. When you look at the corresponding images, of course, they're different. So one of the strategies that is typically used is you look at the synthetic data and you project it onto the real data. By doing that, eventually what you get is more real-looking data, which is good because then you can generalize better. The problem here is going to be that this is a one-to-many mapping, and there are many types of disturbances that are very hard to model. So if you think of lighting or color, that's pretty trivial. You can easily change that. But then you have to model the yarn tension, you have to model the types of yarn, and that's not as easy. So our strategy is to go in the opposite direction. We take the real data and we try to make it look synthetic, which means that it's going to be more regular, and then the learning problem is going to be much easier. So this is the obvious network composition that we come with that. And I want to finish by looking at some of the results. The main catch here, also the main takeaway is to note that we are not just doing texture transfer. There are some pretty complicated physical interactions between the instructions. Instruction you can see on the left of the sections. And so I think there is lots of interesting avenue for doing research that combines program synthesis as well as manufacturing, because at the end of the day, you can use that and you get your new sweater. And if you're interested by any of those, please come to our poster. We have real samples, we have videos, you can touch it, you can feel it. Thank you very much.
These two images are classified correctly. These two are not. The only difference between these is a seemingly innocuous shift. Now, this sensitivity has been analyzed in some great recent work, including in this conference. Inspired by this work, we're aiming to produce a fix. To do so, we must first ask why. Why is this happening? How can shift invariance be lost? After all, we've heard this mantra many times. Convolutions are shift equivariant. That is, the features should be moving with the image, and pooling builds up shift invariance, giving it a little bit of spatial slack. What we'll see is that downsampling, or striding, ends up ignoring the Nyquist sampling theorem and aliasing. Now, striding can be in both convolutions and in pooling, but we'll first start off with an example in pooling. Here's a toy signal, 00110011. Let's max pool it together. The max of 0 and 0 is 0, the max of 1 and 1 is 1, and so on and so forth. And hopefully you're checking my math on this. Now, if we shift the signal by one index, we're going to take the max of 0 and 1, which is 1, the max of 1 and 0, which is 1, and so on and so forth. And we get this output. Now, this answer is very different than this answer, and they were produced simply by shifting the input signal by a single index. What we've done here is we've broken shift equivariance. Let's see if this happens in a more realistic scenario. We can do CFAR classification using the VGG network, and we can probe each of the internal layers to see how shift equivariant they are. Shift equivariance means that you can do a shifting operation and a feature extraction operation in either order. That is, these two operations should be commutable. Now, if we look at the first conv layer, it is perfectly shift equivariant, as we know, and this is a good sanity check for us. But if we go to the first pooling layer, we see this interesting stippling pattern occur. What this means is that even pixel shifts will give the same representation shifted over, but odd pixel shifts will actually give a different representation. And as we go deeper through the network, each pooling layer actually increases the periodicity of the stippling pattern, making things worse and worse. And this is because this layer is downsampling, but it's not taking into account the Nyquist sampling theorem. And this aliasing is breaking shift equivariance through the network. Now, if you recall from your undergraduate signal processing or image processing course, what you may have been taught is that before downsampling a signal, what you need to do is blur it. You need to blur it as a means of anti-aliasing. In deep learning, historically, what we've seen through careful evaluations is that max pooling actually performs empirically better. What we'd like to do in our work is reconcile classic anti-aliasing with max pooling. To do so, we need to look at max pooling a little bit more closely. And our simple insight is that max pooling can be divided into two operations sequentially. One is taking the max, but doing so in a dense fashion, and the second is subsampling from this intermediate feature map. And this allows us to isolate the problem. we can actually keep the first operation because it's not aliasing at all. What's at fault is the subsampling operation, and we can reduce the aliasing in it by adding a blur filter to the intermediate feature map before doing the subsampling. And these two operations can be evaluated together. So this bottom row here indicates our anti-alias version of max pooling. And instead of just one line of code, we can add just an additional line of code to do so. Now, we're motivated, and we have illustrated this for max pooling, but there are other downsampling methods in deep nets as well, such as strided convolution. Now, it's important to note that strided convolution suffers from the exact same problem of aliasing, and actually the same methodology and the same fix applies to it as well. So we can take any network off the shelf and better anti-alias it. So we're going to do that here for a large-scale ImageNet classification test. On the y-axis, we're going to plot shift invariance. So this is the probability that two shifts of the same image are classified the same. And on the x-axis, we can plot accuracy. And here's a whole bunch of networks such as VGG, DenseNet, ResNet family, and MobileNet on these two axes. Now, when anti-aliasing, before I ran this test, my expectation was that we would improve the shift invariance, but perhaps at a cost of accuracy. But I was surprised to see for VGG, we actually saw an improvement in both. And I ran this for all the other networks and saw a similar trend as well. So adding anti-aliasing not only improves the shift invariance, but it also improves the accuracy. Additionally, we've also seen that it improves stability to other perturbations, such as rotations and scaling, as well as improve robustness to corruptions such as noise. So if you're fine-tuning from a pre-trained ImageNet model, for example, ResNet 50, I would ask you to consider going on our website and using our anti-alias version as well. And if you have this snippet of code, stride equals 2, in your network anywhere, perhaps you can benefit also from adding some anti-aliasing. Okay, hope to see you at my poster. Thank you.
So we quickly will decide what is implicit and why do we want to go implicit. Then talk about explicit and implicit, which is basically what IMEX stands for. And I'll not really show results, but you're invited to our posters to see the results. So why are we looking at implicit methods? Well, we know that for CNN there is a bunch of limitations. One of the limitations is for CNNs is the fact that we have a limited field of view. So convolution is basically a local operation, and if you want to go and extend the convolution to a deep field of view, you need to do either many convolutions, or you have to go to a completely different design like a unit in order to get something that will capture large areas of your image at once. And that's really one of the issues that typical CNNs have. The second one is stability. So if you look at CNNs that are completely kind of random, what you'll see that you may have things that growing modes, which will lead to vanishing gradients or zeroing of the final outputs. So all these kind of things are actually well-known problems in different fields as well. And one of the ways to solve these kind of things is by going to something which is called implicit methods. So the way to think about implicit methods is to go and to think about a neural network like a discretization of an ODE. So the ODE I have is on the left. It's basically the derivative of y is equal to the activation function. In this case, it's a simple one of ky plus b. And what we typically do is a forward Euler step, which is written on the right, which is the simplest discretization possible for these kind of things. And you can think about every deep residual network to be exactly these kind of things. So forward Euler is a great method, but it's not that great. It's a very old method, and it doesn't really give you much in terms of stability and a lot of other accuracy, a lot of other things. And we know that in order for forward Euler method to work well, it requires small enough steps, which actually translates to either taking many steps in order to go further, or to having the norm of the convolution kernels to be relatively small for stability reasons. And that's the reason why we see in many cases, again, exploding gradients or vanishing gradients or these kind of things. So what can we do? Well, typically what people in science and engineering do, they come and they use implicit methods. So implicit methods, what they do is rather than say that we compute the next step at iteration n+1, we actually go ahead and put the n+1 inside the bracket. So I'm not going to tell you the long story here. The long story will be at the poster, but that gives us a different design of a network, which is written here on the right. And the different design require a little bit more work, which is inverting a matrix, which can be done by Fourier methods. And I thank the previous author by exposing basically Fourier transform here in order to compute the convolutions. But when you do these kind of things, two things immediately happen. you get immediately a full range of view of the whole image. So in one step, you see the whole image, even though you're using something which is just a 3x3 convolution vector here, because you're looking at the inverse of the matrix, not the multiplication with it. So that's one thing. And you gain stability from these kind of things. And these are methods that are very, very common in computational fluid dynamics, computational electromagnetics, nonlinear dynamics. Anything you go around, you'll find out that these methods are one of the most common and used methods in order to solve problems in science and engineering. So again, come to our booth at going to be poster number 140, and I have chocolate to everyone who comes and want to actually have something. That's the other way to convince you to come to our thing.